Welcome to Altium Designer PCB Rules. In this module, we will learn how to generate rules for the PCB using a few methods. While I mentioned it in an earlier module, rules are what drive the PCB layout. The phrase rules rule is most certainly true within Altium. Let's open up the Rules Editor panel by going to the Design pull-down menu and clicking on Rules. This opens up the PCB Rules and Constraints Editor window. Rules are stored as part of the PCB document. This provides portability of the PCB file as it carries with it the associated rules. We can see that rules are organized into 10 subcategories. On the right side of the window are all the rules listed with two important details showing their priority and whether or not they are enabled with the Enable checkbox. We will talk about priority a little later. The Enable checkbox allows for a rule to exist but not be enforced. This is an important consideration. Normally, I do not disable a rule as I would not want to inadvertently release a PCB with disabled rules. One exception in this case is the test point rules have been disabled since I'm not going into production for this particular design. There are two types of rules, unary and binary. Unary rules define a standalone attribute like trace width, whereas binary rules cover interaction between two objects like the clearance between tracks or components. Diving down into the electrical category by left-clicking on the arrow, we see the priority values and enabled checkboxes. Expanding the electrical rules shows us the rules grouped under this category. As expected, clearance, short circuit, and unrouted nets, unconnected pins are listed along with modified polygons. Examining the clearance rules might help clear up a few things. The number 1 is the highest priority rule and is the first in line, taking precedence over all the lower rules. The lowest priority rule we see here is the default clearance rule at priority level 5. Double-clicking on the lowest priority rule shows us the details, starting with the rule name. And now let's look at the scoping qualifiers. Clearance rules are binary types and cover the interaction between two objects. We see that both the first and the second object matching scope is set to all, meaning all of the objects would be selected. Rules are targeted or scoped using the object matching queries to select a particular object like a 12-volt net, or a group of objects like all. Please fight the temptation to edit the default rule, like I'm doing right now, for some particular need like a high voltage net requiring a larger clearance. Cancel out of this and reopen the Rules Editor to show you how you actually should do this. Instead, we should right-click on the default rule and select either Add a new rule or duplicate the existing rule. If there was only the default rule and it was edited to target a single net like 12 volt, then all the other nets would have no clearance checking performed when running DRCs. This trap has caused more than a few PCB coasters to be created. I say coasters because all they were good for was placing under coffee. Now with the new entry, we can safely edit it and not affect the default rule. Let's add the clearance for the 12-volt net here. First, rename the rule. This makes it easier to find and provides insight for others. Clicking on the name and change it to 12-volt clearance. This makes the rule purpose obvious. We could further narrow the focus of this rule by changing the second object matching field. Using the pull-down menu, there are a few options as you can see: net, net class, layer, net and layer, and custom query. Let's keep it as all for now, as that makes sense in this particular rule. We want to have the 12-volt net to have a minimum of 30 mil clearance from all others. We can set different values for the clearance rule using the table and directly entering the needed changes. Simply left-click and then type the new number. Notice the upper minimum clearance has changed to NA, indicating that there is more than one value entered into the table. To have even more control, click on the Advanced button. This expands the table, giving us a 9x9 set of options for setting. Having this fine-grained control allows the rules to be customized extensively. It is very important here to note that if the default rule with the scope of all is at a higher priority than all the other rules, this would have significant implications. With the scope set to all and all, this rule would apply to all objects for clearance. The effect would be to prevent all of the lower priority rules from being enforced. In particular, in this setup, the 12-volt clearance rule settings for the 12-volt net would not be in effect because the default rule with all has a higher priority. Let's fix that. With multiple clearance rules, we need to ensure that the order of the rules applied makes sense. Clicking on the Priorities button allows us to change the current group's rule priorities. We can review and change the clearance rule priority order by selecting a rule and increasing or decreasing its priority, as you can see here. I use a fishing net analogy to describe the effect. Whatever the scope of the highest priority rule includes or catches does not get passed down to the lower priority rules for checking or enforcement. In this case, nothing would be passed to the 12-volt rule check and only the default rule would be enforced. Changing the priority makes the 12-volt net object get caught first, and the rule for 12-volt clearances is now applied. Any remaining objects not caught by the 4 higher priority rules would be, in fact, checked by the default rule. Hitting the Apply button reorders the rules, showing the updated priority. Looking at the object matching options, we see the Net Classes option. Altium uses net classes as a convenient way to group objects together for design rule creation. There are a number of classes in Altium, including nets, component classes, differential pair classes, PCB layer classes, as well as those associated with buses and others. Net classes can be created using schematic directives, as we saw earlier for the differential pair net directives. They would generate a differential pair class by default. Let's open up the power supply schematic, and let's add a new class called Power Nets in this schematic using the Net Class directive. To do this, click on the Place pull-down menu, select Directive, and then Parameter Set. Moving over the schematic, we can hit Tab so we can now name the new net class prior to placing the directives on the schematic. Fill in the directive label and the net class name as Power Nets. If we wanted to add a rule here, we could, but for the purpose of illustrating adding the rule and using a net class from the PCB perspective, we will add that from the PCB rules window. Update the PCB from the schematics using the design update as we had done earlier. Notice the new class definition being added to the PCB. We'll not add rooms to the PCB, leaving the ECO enable checkboxes unchecked in this case, as the layout has already been done for this particular example. Back in the PCB view, open up the rules and navigate to the routing category and expand it to open up the width rule. Right-click and then add a new rule, naming it Power Nets. Now, using the Object Matching pull-down menu, we select Net Class, and then we look for our Power Nets class. We could now edit the width parameters as desired and, if needed, use different width values per layer. This might be needed, for example, if they were differing copper weights for the layers, say inner versus outer layers. Hitting Apply or OK sets this new rule up. Again, be sure to check for the priority and don't use the default rule, but add or duplicate a rule. Now we've looked at rules and added rules based on a net class from the schematic as well as manually from within the PCB. Remember that rules can be added to the directives themselves from within the schematic, as we saw in Module 13, transferred to PCB. Placing directives in the schematic with rules defined can improve the communication of the design intent between the schematic designer and the PCB designer. Using directives to create net classes in the schematic without adding the rule definition allows for the PCB designer to properly engineer the needed rule parameters based on the PCB's physical attributes, like trace width based on current requirements. Having the net class defined, the designer could now include instructions for the net class on the schematic. For example, by placing text. Again, a note for the PCB designer. To add or check for net classes within the PCB, left-click on the Design drop-down menu and then Classes to open up the Object Class Explorer window. Here we see all the classes that are currently defined. We can create new ones as well. To see the defined class objects, left-click on the class. To create a new class, right-click on the Nets class entry and select Add Class. Then rename it by clicking on the Name field. With this new class added, we can pick which nets are in this new class. Selecting a net, we can just add it by clicking on the single greater than sign, or all of the nets by clicking on the double greater than sign. In that case, all the nets move in the desired direction. So to move one net or all the nets from one window to the other, you would simply click on the greater than or double greater than, less than or double less than sign, depending on which direction you are moving. If you create a new net class in the PCB, it is important to remember that further updates from the schematics may want to delete these new classes, as they do not exist in the schematic. So be careful with future updates and disable these added class deletions before executing the ECO. How do you create custom queries for use when targeting rules for specific objects? One easy way is to use the find similar object method to create the query. Selecting a component, in this case the Anderson connector, and right-clicking causes a pop-up menu. We select Find Similar Object, or FSO. We can use this window to create an expression for use in a rule. Selecting Same for the footprint. Now we make sure that the Create Expression box is checked. This will, of course, create an expression that we can use later. Now hit Apply and see if all three targets are selected. Excellent. Click OK to close this window, and we shift our attention to the PCB filter window that just opened. Here we see the query expression in the filter window that we had generated from the Find Similar Object. Hitting Apply to All with the Select button checked will select the connectors and mask the rest of the PCB. To clear this masking, hit Shift and then C. You can either copy and paste this into the rule or click on the Create Rule button to open up the rule type selection window. What we are looking to do is create a rule that allows the red Anderson connectors to butt right up against the black Anderson connectors. So we would pick Component Clearance Constraint Rule. This opens up the Rules Editor window with the new rule populated. Editing the name to Anderson Clearance and setting the minimum clearances to -5 mil, which is the required overlap of the models. Now, with the rule partly defined, it is important to see if the rule scope is properly targeting all of the intended objects and no others. To test this, and to illustrate a nice feature in the Rules Editor window, we will use the Test Queries feature. This opens up the Test Queries result window, showing each expression's results. Clicking on the first object query shows us which objects are active for this rule's query. Note, the second object query lists a large number of objects. This is because of the all that is still in that query. Let's hit Close and tighten up the second query to point to the red Anderson connector footprints. As I know the footprint name for the red Anderson connectors, I can copy and paste the black footprints query into the second query window, and then we can edit the name. Now when we hit the Test Query button, we see 3 in each query. Selecting the first and then the second, we can identify which components are affected by this rule. Yes, we can see that we've targeted the red and black Anderson connectors in each of the queries. Opening up the PCB Rules and Violations panel from the Panels menu, we can test the new rule we just added. This panel, the PCB Rules and Violation panel, is very helpful when clearing up DRCs on your PCB. We will see this again in a future module. For now, left-click on the Component Clearance Rule group. This shows us all of the clearance rules. We can run the group using the right mouse button and picking the Run DRC rule class. We see there are no errors for these components. One more method to generate rules is to use the Altium Rule Wizard. This can be found on the Design pull-down menu. Here we can name the rule Power Width and add comments if needed, and then select the rule subcategory to add. We'll select Width Constraint. Let's add a width rule to a couple of nets, starting with a 5-volt net. First, we select the condition type by left-clicking on the triangle and selecting Belongs to Net from the menu. Now in the condition value entry, use the drop-down menu and select the 5-volt net. We want to add another net to this rule, so by clicking on Add Another Condition, we get a second entry along with the default AND operator. Note there are a lot of options here, including layer, net class, etc., that could be used in the creation of a more complex rule. With the 12-volt net added, having the logical AND of the two queries would never work. We can't have both a 5-volt and a 12-volt net at the same time. We want both of these to be active, so we need to change the AND to OR by left-clicking on it and selecting OR. Now we would apply this rule to both 5-volt and the 12-volt nets. While we're here, we can build up levels to the rule by selecting the group and clicking the right arrow to enclose them in parentheses. We could now add more operators and conditions to further refine and tune the rule entry. As you can imagine, this can get quite complex. Hitting Next, we have a chance to review the relevant rule priorities. Assuming that we like the current priority settings, hit Next and we can see the final rule is created. If we want to edit the default rule values, before we click on Finish, ensure that the Launch Main Design Rules dialog checkbox is checked, and then we can click on Finish. Now we can change the rule values in the rule editor, just like we would normally edit them. This concludes Module 19, Altium Designer PCB Rules, where we looked at various methods for rule generation, as well as testing the rule queries in preparation for working in the PCB. Rules drive the PCB routing and checking for all of the PCB elements. Having the rules set prior to starting PCB placement and routing will save the designer from needless rework. Please do exercise PCB rules.